All right. Thank you. Thank you. Uh, Thanks a lot. And I welcome everyone who is connected or sure, I can share the coffee. Definitely I can. It's too bad actually to have the coffee alone. So please be my guest and let me virtually share it. Where is my video? So there we go. The cup is on Starbucks, but the coffee is not from Starbucks. So please excuse me for that. Okay. So thanks everyone. I'm going to stop the video. Thank you for having me. Thanks for the opportunity. And I welcome everyone who is actually in the session. Thanks for joining in. I'm going to stop the video just to keep the bandwidth saved. Okay, so my name is Aman Sharma, and this session is about back to basics, database buffer cache. So this is the session about somewhat more details about buffer cache, which every DBA should be already knowing about. So let's get started. So this is about me. Um, my name is Aman. I have been using Oracle database for more than 15 years now. I'm an Oracle ace. I was the first Oracle ace in India in database, and I have been on the Oracle forums. Uh, I was the vice president in the All India Oracle user group, and I founded the first regional chapter of the same group as well. And also, I tweet here, I blog here. I'm co-author of two books, which I mentioned here. Written with one of my friends, Kamran, and my friend Francisco, and bunch of certification logos, which I just put up over here. So before we start, this is the slide that we are supposed to actually mention and talk about, which is actually about the ACE program. Very, very important and probably the most prestigious thing that, at least I have achieved in my career, having an Oracle ACE award. Oracle ACE program is actually the recognition program from the Oracle, and this Oracle ACE program has 3 tiers, an ACE Associate, an Oracle ACE, and ACE Director. And this program is basically to recognize people in terms of their contributions to the Oracle community. So if you are actually someone who is finding it really, really good to share your technical knowledge in terms of giving presentations like this one, or writing blogs, writing answers on the OTN forums, or doing how-tos, recording videos. Anyway, you actually help Oracle community. So you can actually be a part of this program. So you can actually nominate yourself, or you can ask someone to nominate, you. There are 3 levels for this. ACE Associate, which is basically the starting level. This can be upgraded to the Oracle ACE by the Oracle ACE program team. Jennifer and Marwa, they basically handle it. An ACE Director, which is actually the last level, which is more of a sort of like a direct link of you with the Oracle's teams of a certain product, and you are actually going to be recognized as a leader in terms of the tool or product that you're actually using. So if you're an ACE Director in database, that basically is going to be recognizing you as a leader in that particular domain, and you will be actually able to put forward your ideas and Oracle community ideas to Oracle and bring their response back to the Oracle community. So with that said, this is actually one of the very important slides. So this is actually the entire stuff that we are going to be talking about in this slide is basically going to be, my own understanding. I don't have the access to the, source code or something. So all what I actually mention over here in this presentation is basically my understanding about buffer cache. So whatever I say, do pick it up with a big grain of salt, which is what I am trying to mention over here. So do pick it up with a big grain of salt. Now, this is basically the agenda or the lack of it. So we're going to talk about buffer cache. We are going to talk about a little bit more about buffer cache, which is actually, what the main crux is. And the last bit is actually going to be about buffer cache tuning. So that's basically there. Okay, the screen is not showing. Got the message. Screen is not showing. Is the screen moving or not? Or let me try to stop the share and do it one more time. Panelist, if you're there. Okay. Let me stop the share and bring it
We
one
are
more
here
time.
and slides are moving.
Yeah, I've just shared it again. So please, if I can actually get the confirmation if the slides are moving. Can you see the animations and everything moving?
Yes, we see.
Okay,
Yes, yeah.
great. Okay, great, Furkan. So great if you got it. So we got two raise hands actually. Can we have the questions in the end because we're on a tight time schedule actually. So please mention your questions and the panelists are actually going to probably mention it to me in the end of the presentation so that we don't run out of time. Okay, so this is going to be a quick introduction to the Oracle instance. This is basically the instance part. So obviously in the instance, we have a lot of memory structures. The instance is actually going to be on the RAM. And then we have the structures on the disk, which are actually going to be the physical files. So we have a bunch of physical files. We have the database, which contains dictionary. And of course, we have the standard, applications, listener, which are connecting to the server process, the PGA, and so on and so forth. Now, the one of the structures within the instance is actually going to be a buffer cache. Now, in terms of every particular part of the Oracle database instance, especially the memory structures or even the normal working, they are basically going to go through a kernel architecture or a kernel layer architecture. That basically means that whenever we do something in the Oracle database, the processing actually goes through in various stages actually, and those stages are maintained by a different set of layers. Now, these layers are actually going to be important and they are actually going to be exposed in the X dollar tables that we are actually going to be having in our system. So, for example, there is a table that I'm mentioning here, KCBWDS. Now, this table does not really make much sense right now because it is actually an acronym. But if we do know that what this table is actually linked to in terms of the kernel layers, then it will make much more sense. So this K obviously stands for kernel, this C stands for cache, this B stands for buffer, WDS we are going to talk about. And how do we actually know this thing? Well, these layers are basically going to be available here. So you can actually notice that I have put up the kernel cache layer, which is actually the KC layer. And this KC layer is actually the layer which basically works or which basically controls this particular buffer cache. And there are many more layers. For example, there is a transaction layer for transactions. So you have the tables X dollar, KT, UXE, CXP, so on and so forth. So those particular tables are actually going to be the part of different kernel layers architecture. Now, what is buffer cache? Now, this is actually a quick run through. Buffer cache is the memory representation of the data which is accessed from the disk. It is created basically to get you the data in terms of the fast manner, because as a golden rule, anything which you access from the disk is actually going to be slow. Anything which you access from the RAM, that is actually going to be faster. Now, this does provide you to get different kinds of data types access or block types access. You actually do get the data in terms of consistent manner or in terms of current manner. Consistent are basically going to be required for the read consistency. So if you're going to be doing read consistency, Oracle creates something called the CR blocks, or if it is going to be rack, they create something called the past images, which is actually going to be used in terms of the cache fusion, and that also serves the purpose actually of the multi-versioning or the multi-versioning concept. Now, this is a circular cache, which means that it is not going to be a cache which remains similar all the time. It's constantly going to be flushed out, and it is actually going to be flushed out by the LRU algorithm. Now, this name is actually a generic name, and we're going to talk about that, but this is actually a generic name. It's not really actually the algorithm name per se, and it is going to be something which is based upon a touch-based algorithm. Now, it does have a flushing mechanism which is based upon checkpointing. We're not going to talk about checkpointing here, but the checkpointing is going to be incremental, which means after every few intervals, the checkpoint is actually going to happen. Now, the buffer cache in the old times when the database was actually of the versions before 9i was actually going to be made something like this. So you basically, had the database buffer cache available as a singular cache, which was basically maintained as one single unit. And within one single buffer cache, you had the other two caches available as well, which was actually the keep cache and the recycle cache. So you have one cache which basically holds the data by default whenever the data comes from the disk to the cache. This particular data is going to be this cache is going to be for the actual data whichever you're going to be accessing. But if you want to keep the data available for a little bit longer, then you can use the keep cache. And if you want to actually get the data flushed out very quickly, then you can actually use a secondary cache called recycle cache. Now, the keep cache earlier and the recycle cache, they used to take the memory from the default cache itself. And this entire thing was actually static, which means that if you wanted to change any component size, it was not available to you. You had to restart your database. This did get changed in terms of the system, and you basically have now the entire cache available as in terms of something called the dynamic cache or dynamically maintained cache. So now each of the cache is actually going to be a separate structure altogether. So you have a default cache which is still going to be there, but now this does not give the memory to the keep or to the recycle. So they are created as separate caches in their own entirety. Plus, these caches are now going to be dynamically possible to get resized. And also, the memory allocation of these is now going to be done with the help of a memory chunk, which is actually going to be called as granule. So take granule as like a unit of the memory. So you basically are going to be having such kind of structure. So you're basically going to be having a granule, which, for example, is of 4 MB, and you are going to be allocating multiple such granules basically to allocate the memory in terms of these caches. And besides these caches which we have over here, we also do have the caches for the non-default block size as well, which is actually for the transportable table space environment. So these are the parameters which are basically going to be there. So the buffer cache, unlike the shared pool, is actually a cache which is basically maintained by a default unit of the memory and a static unit of memory, if I can say. That means if this is the buffer cache, every chunk of this cache is going to be maintained of the same size, which is what is the reason that in the buffer cache, you don't get 4031, which is actually an error, which is very popular in terms of the shared pool. And the basic reason for that, that in the shared pool, you are actually going to have these chunks of non similar sizes. So one chunk can be of a bigger size, second chunk can be of a smaller size. And because of this, this buffer cache does not get actually the 4031 or insufficient memory error. Now, these chunks are controlled by the parameter db block size, which is by default set for 8 KB, and you actually can have it in the variation of 2 KB to up to 32 KB. 8 KB is the default size, and this is actually going to be the size for the entire set of the pools. Again, the db keep cache and the recycle cache, they are not by default configured. You actually, because they're all individually allocated, that means you can actually go ahead and set up this particular 3 caches separately if you want to. Non-default caches are going to be again maintained by a separate parameter. Now this is up till now should be actually something that we already must be aware of. Now in case you want to use these keep cache or recycle cache for some of the objects, for example a table or index, what you actually can do, you can basically put that particular object in the storage clause, the parameter called buffer pool, and you can actually mention over there the keep cache or the recycle cache. Now, the keep cache is actually going to be the cache which is controlled by the parameter db keep cache size. Now, this is required basically for those kind of environments where we do actually need the cache to be available or the object to be available for a more longer duration as compared to the default cache. That does not mean that the default cache, the keep cache will not actually be buffered or flushed about. It is actually going to be, but it is going to be slightly delayed as compared to the default cache. This is not auto-tuned, which means it is not going to be having auto-tuning available as what we have available for the default cache. And it is going to be using the similar mechanism of the LRU as of the default cache. Then we have something called the recycle cache, which is maintained by the DB recycle cache parameter. Now, this is something which is again going to be not by default configured or required unless we are going to be having a requirement of a cache or for an object where we do not want to keep its data at all in the particular system memory. Now, this can be those objects which we do not access for very frequent times. This can be those kind of objects which we do not need to be cached pretty much in terms of our system at all. So those objects actually can be a part of this particular recycle cache. Again, this is not auto-tuned, and this is obviously not going to be a part of default mechanism. Yes, the error of 4031 does not occur in the buffer cache, and the reason is I cannot explain the reason in more detail here, but because the shared pool is actually able to have, in a very brief way, shared pool is actually able to have basically something called variable chunk size allocation. So what I mean basically in that is that in the shared pool, if for example I'm allocating a particular cursor, so this is going to be allocated in terms of chunks, and these chunks are actually going to be in variable sizes. So if I need, for example, 8 KB of the chunk, what the shared pool memory allocator can do, it can basically allocate for me a 2 KB chunk, and then it can allocate for me a 6 KB chunk, depending upon which chunks are actually available as free. Now, if it is allocating a 2 KB chunk and a 6 KB chunk, and in this 6 KB chunk, it is not able to find, for example, this 2 KB of the memory, right? So then it is going to say to me that I have 2 KB allocated, I have 4 KB allocated, but I cannot find the 2 KB. And for this 2 KB, it is going to be throwing at me 4031 insufficient memory error, and it is going to say to me that these many number of bytes, which is the 2 KB bytes, not found in the shared pool. Because in the buffer cache, this kind of variable chunk is not allowed. And 4031 is not limited to shared pool. Any particular memory structure which actually can have varying chunks possible, they can all have 4031. It is actually an insufficient memory error, not linked directly to the shared pool. It is basically going to be for any memory structure. So we can have it for large pool. We can actually have it for Java pool or any particular pool which possibly can have a variable chunk. Does that answer the question? Great. Thanks. No problem. Okay. So then we have the non-default chunks available, non-default caches available. The non-default caches are basically for the non-standard block sizes. So from 9i, Oracle has the support that we can have the default block size as 8 KB, but we can still create a table space of 2 KB or even 16 KB. Now, there has been a lot of talk about that, whether this is for performance or for what purpose, but this is actually meant for the transportable table space. And the reason actually is that maybe in my source system, I have the 8 KB as the table space, blocks size. But in my target, where I want to move my table space, the block size is 16 KB. So I can have my table space available in 16 KB locally, and then I can move it to my target database, which is going to be of 16 KB. It is not really meant for performance. We can sort of loosely link it to performance if we want to, but it is not really going to be something that we should really believe into. Now, the entire granule structure is basically going to be, as I mentioned, is going to be like a memory chunk available to us based upon the SGA sizing. So depending upon the SGA size, we actually will have the chunk size of granule available from 4 megabytes to 16 megabytes. We can actually check it out in the SGA info, what is the current granule size available to us. Now it is available publicly, earlier it was not. And every memory chunk which is allocated to us in terms of the memory structures, it is basically available from this granule structure itself. So this is the granule structure which is going to look like from the buffer cache part. So every buffer which is actually going to be accessed, basically for that buffer, or at that block, I should say, for every block which is accessed, Oracle is going to be holding in the granule an array of the buffers, which are basically going to be the header copies, and the arrays of the blocks, which are basically going to be the actual data. So that means that we are going to be having like this linked list sort of, and this linked list is basically going to be the particular linked list which contains the metadata for the buffers accessed and the data of the buffers accessed. So when we say the buffers are hot or the buffers are cold, that basically means that the buffers are actually tracked based upon their status that is in their buffer headers. And when we say the buffers are flushed out or something, which is actually going to be the one, again, we are going to be saying that this is going to be something that maintained in terms of their headers. Now, in terms of the buffer cache being maintained, so this is going to be done in the form of a hash table. So basically, the buffer cache is maintained in the form of a hash table, and this hash table is going to be maintained in a key value pair, which is actually generated with the help of something called DBA, data block address, and the table space number. So that means that if I have a block, for that block, there is going to be a data block address generated. And this data block address is something which is actually going to be used by Oracle to hash the block and then allocate that block in the system. Now, these hash buckets are basically going to be like containers. So let me just quickly show you that before I jump into this. So this is how the buffers are basically going to be there. So we have this buffer cache. We have the hash bucket table. So these are basically the buckets. Now, these buckets are going to be having something called chains. So each bucket is basically going to be having kind of a string available. This string is where the buffers are sort of like hung, right? So this is like a rope, or you can say a cable on which these buffers are basically hung. And these buffers, which are basically created, they are maintained based upon their DBA in terms of the bucket. Now, buffer status is maintained in these buckets for different buffers. So if you are going to change a buffer, for example, a buffer is a clean buffer, and then the clean buffer becomes a dirty buffer, and then someone requests the same buffer for the access, this dirty buffer is going to be now given to that person as a CR copy. So this CR copy is maintained actually in the same bucket, which is actually going to be the bucket where the original dirty copy is going to be maintained. Now, to access the buffers in this hash chain, we are going to be using something called the cache buffer chain latches. Again, the cache buffer chain latches are basically going to be the latches which earlier were maintaining one particular latch for one bucket, but now it is 1 to n. So one particular latch is able to maintain more than one, and you can actually configure these buckets and latches actually by these parameters, but you're not supposed to. Oracle says that this configuration from long time back is no longer required to be done manually by the DBS. But if we do actually see the CBC latch coming too much into contention into our particular system, that means in our AWR or something, that means there's a lot of requests coming by people to access the buffers from the buffer cache. And that does mean that we do have the buffers which are actually very hot, and we are requesting them again and again. So that can be one of the things which we can possibly look into to tune the buffer cache. We'll talk about that in the end of the session. Now, buffer cache is maintained by a couple of structures which are maintained internally for it. So there are going to be descriptors. So now we know that there is a kernel cache. KC is kernel cache layer. B stands for buffer. So this is WB work area buffer pool descriptor, kernel cache buffer, work area descriptor set, buffer header, which is going to be there, and buffer descriptor. So this is descriptor set. And then we have the LRUs. So each particular buffer cache structure is maintained in the form of pools, which we already maintained. Now, these pools are basically where the entire buffer cache is going to be organized into. So basically, each buffer pool is going to be getting a header, and these header descriptions are in this particular structure. And what Oracle does, they sort of divide the buffer cache into smaller chunks, which are basically called work area set. So what I mean by that is, if we have this buffer cache, we are going to be having in this cache uh, small chunks created, and each chunk is going to act as an independent buffer cache. So each chunk is going to act like an independent buffer cache. Now, why this is done? Because the buffer cache size can be very huge. So it is not really going to be good if we are going to be having a 50 GB, 100 GB of the buffer cache. We're going to scan that cache as a single entity. So it is not actually going to be a good thing. So the entire cache is divided into smaller chunks, and then based upon that, we are basically going to be able to manage it. So this is what we are going to be seeing over here. So the buffer pool is going to be having granules allocated. These granules are going to be having work areas used, for them or within them. There are multiple work areas possible, and I believe it is going to be based upon the CPU count. We'll see that part just in a minute. And each work area set is maintained by DB writers. So when we say the DB writers are actually going to be writing the data out from the buffer cache, it is actually going to be in terms of multiple work areas or work area set. So whenever we say that DB writer is not enough, that means that we are not having enough DB writers to maintain basically the work across all the work area sets. And that is why in a multiprocessor system, it is recommended to have multiple DB writers, because it could be actually possible that multiple work area sets are there, but they are maintained by a single DB writer, which of course cannot manage all of them in terms of an optimal manner. Now, the maintenance of the buffer cache is done in the form of buffer headers. That is why we don't have the $BC. We don't have $BC. We have $BH, which is buffer header, because whenever a block is accessed from the disk, it is maintained in the buffer cache in terms of its headers. That means there are headers which are actually going to be maintained within the buffer cache in different linked lists. And these headers basically maintain this information. So each header is going to have the address, the chain it is going to be linked to, and which particular position it is actually going to be there, like it is in the LRU or in the MRU. And it is also going to be having information that whether you're actually able to access the buffer or not, or what is the current flag on that buffer, whether it is a dirty buffer or it's a clean buffer, so on and so forth. That is why the entire buffer cache management is done in terms of the headers, not in terms of the buffer cache itself. So each work area set is a logical division. If it's going to be there from 815, and this is maintained by something called the LRU chain latch. So we have two latches. One is the cache buffer chain latch, and one is the cache buffer LRU chain latch. Now, I just mentioned that the cache buffer chain latch is basically to represent whether we have a hot buffer contention or not. The LRU latch simply means that we are now looking for the buffer to be allocated from the buffer cache. That means if I want to load a buffer from my disk, let me go back to the previous. So if I want to load a buffer from the disk to the buffer cache, I need to find out for this particular buffer a free buffer in my memory structure of the buffer cache. Now this finding out the free buffer is done by the cache buffer LRU chain latch. That means if we do find out that there is a lot of contention, or this cache buffer chain latch, LRU chain latch is actually being shown in my AWR in the top 10 events, that means I am actually not having enough free buffers in my particular buffer cache. That means that I'm running out of the free buffers for whatever reason. Maybe I have a small cache, maybe I have a suboptimal DB writer number, maybe I have a suboptimal storage space. Anything, it actually can be the reason. So each work area set is going to maintain multiple LRU chains, and it is going to be also having the checkpoint queues, which are basically from where the buffers are going to be written out. And these particular work area sets are exposed in this table $KCB WDS, which is kernel cache buffer work area descriptor set. Now I have mentioned this as 2 into CPU count. The last I checked that the number of work areas are actually based upon the CPU count multiplied by 2. But again, That's the reason I mentioned the disclaimer that we need to confirm that whether this particular formula is still going to be the correct formula for the latest versions or not. It was, but I think I didn't check it out for the 19C and for the 20C. Don't have the access of 20C anyways. So now, in terms of the buffer cache, one of the topics which actually does come very often is the linked list discussion, that we have a hot buffer list, we have a cold buffer list, we have a dirty list. And this is sort of like it is actually maintained that, we have a linked list, which basically is of having a hot end and a cold end. We have a linked list, which is actually having the dirty buffers. Uh, and this is how it is actually represented in most of the classrooms or in terms of the discussions. It's very easy to understand, but it's not really correct. And basically, in terms of the buffer cache, what does Oracle do? They do not really have such kind of feature of having something called a hot or cold, which is, if you really think about, is really not making sense, because we can't really have a hot end of something, or hot RAM, or we can't have a cold RAM kind of thing. That's just not possible. So what we actually do in terms of the system, we are basically going to be having this thing that we are going to be having multiple linked lists, and multiple linked lists are actually going to act as this hot and cold end. So we do have a linked list, which is going to be sort of called as hot list. We do have a linked list, which is going to be sort of known as cold list. And the buffers are attached from the disk to this hot list first. And if you don't use the buffer for some time, then that buffer basically gets attached to this cold list. And if you don't use that buffer again in this cold list, then that buffer is sort of like flushed out. It's basically going to be now, thrown out in this, whatever infinity space. Now, this particular name is not correct actually. This is more of a understanding, purpose name. There is a main list, and there is going to be an auxiliary list, or aux list. And since it is maintained in the name of LRU, so there is a LRU main and there is a LRU aux. So let me quickly wipe it out. So basically what we have a buffer cache. In this buffer cache, we have this main list, we have this particular aux list, and we have the checkpoint queue list. So basically what happens, entire structure is maintained by the LRU chain latches. The buffers are linked to the main list, as you can see. From the main list, the buffers can get detached and get attached to the cold list. They can go back to the main list if you access them again. And if you make them dirty, they're going to be detached, sorry, from the main list to the checkpoint queue list. And from there, they're going to be available to get flushed out from the particular system. Now, and again, the LRU chain latches are available by this parameter, db block LRU latches, not again required to be changed, but still possible. And this structure, which we have for one work area set, is available for the entire buffer cache, which means all these linked lists are going to be available in terms of entire work area sets available across the buffer cache, right? Now, that brings us the particular set of the table. So actually, if you notice in the Xsolar KCB WDS, there is actually called NXT REPL and NXT REPL AX, which is actually the aux. So this is the main list and this is the aux list. Again, it's not really required to look into that, but if you actually check it out, this is the so-called hot list and this is the so-called cold list. And if you actually dump the buffer cache, you actually can see some of these things actually mentioned in terms of the buffer cache dump as well. So what I'm trying to show basically is that, we do have a buffer header, we do have the replacement queue, we do have the touch count, which I'm going to talk about just in a minute. So this is the touch count, and we do have a checkpoint queue and so on and so forth. So we can actually see the buffer is marked as a hot buffer, and we can actually see that different linked lists are actually mentioned here in terms of system. So we do have a checkpoint queue, we do have a file queue, we do have the flag and other things actually there. So all of this is basically possible if we actually dump the system, and we can actually check it out in the background. Now, The buffer cache is maintained by the LRU algorithm, which is what I mentioned in the previous slide. It's actually more of a generic term, and the reason for that basically is that the LRU algorithm is basically the algorithm which is used as a term for any memory structure access. This basically means that any memory structure that we actually have, we are basically going to manage it by some sort of LRU algorithm itself. And this is the same thing that we do actually have in terms of the buffer cache as well. But the buffer cache basically started with this LRU algorithm itself. Now basically, what is an LRU algorithm in a brief? It's actually a big linked list which is actually going to be there, and the same way buffer cache was also maintained in the past, or you can say in the original release of the database. So it's a single chain, it's a singular chain which we actually have, and this chain is basically going to be having two ends, a hot end and a cold end. And this is the representation which is still very popular in terms of many classes of the DBAs, where the basics actually are taught for the database buffer cache. But and it is still true. But this particular LRU algorithm was actually having some trouble, and that trouble basically was that this particular structure is actually going to be having problem when we are going to be doing a lot of full table scan, because it's actually going to be one single chain. If we are going to be having this entire chain basically available to us and we are going to be doing a full table scan, what is going to be happening that we are going to be flooding this entire particular chain with the objects or with the contents of that one big full table scan, which obviously means that other tables or other tables contents are basically actually going to be flushed out. So what Oracle did, they basically changed that and they added this algorithms modification from the version 6, and basically that version change introduced the parameter of this small table threshold. So now this entire thing is going to be maintained in the same way, but a small window was actually added basically. And this small window is going to be the full table scan window. So if your table size is going to be in between of this particular window, which is maintained by this particular small table threshold, that means you are actually going to be having your full table scan controlled by this particular FTS window. So the normal scans actually would go to the rest of the linked list, and the full table scans are basically going to be linked actually in terms of this particular part. Now again, this was working very very fine, but this also could be sort of like could be abused, because if you're going to be doing a lot of scans basically for indexes or such, you are still actually not able to access them, maintain them properly, because again you're going to be accessing them in terms of a lot of scans. If you're doing an index fast full scan or so, they're still going to be considered as a scan only. So this was actually changed by something called a touch count algorithm. So now what Oracle does, they basically maintain in the block a header. In that header they maintain a counter, and that counter is known as the touch count. So sort of like whenever we access a buffer or we touch a buffer, this counter is incremented to 1, then this is incremented to 2, so on and so forth. Now based upon this particular counter, the buffers are going to be promoted or they're going to be demoted, and their eviction is also going to be based upon this only. Now to make this counter not to increment exponentially, there is going to be a timeout which is again controlled by a parameter, and this timeout is a 3-second timeout. That means if we access the buffer now at 1 second, we should be waiting for 3 seconds, and at fourth second access this counter will be incremented, and next will be at 7, and so on and so forth. And this counter is going to be exposed in this particular table XOR in the column TCH. So that means now when you're going to be having this particular cache, we are going to be having the LRU linked list, and this linked list is now going to be having sort of a midpoint, and this midpoint is basically the point which is actually now considered as like the point from where the buffer is going to be promoted from being in the cold end and then going into the hot end. And this promotion, as I mentioned, or even the demotion, is based upon how hot the buffer is, and the hotness of the buffer is maintained by the parameter, by the value of the touch count. So this is going to be done like this. So you're going to be having the touch counter. If the counter is incrementing, that means the counter is going to be checked by the system. As soon as the counter becomes more than or equal to 2, That means the buffer is now going to be marked as the hot buffer. Now, as soon as the buffer is going to be marked as hot, there is going to be a, this is wrong, it's actually going to be 1. So there is going to be a cool down effect. That means now your buffer is a hot buffer. Oracle does not let the buffer be remaining as a hot buffer. They're going to cool it down. This cool down is going to bring the counter down, which is going to be that the counter is going to become, artificially removed or demoted to 1. If the buffer is not accessed after being cooled down, it is going to be now a buffer, which is now going to be considered as a buffer for being available for eviction. And this increment or decrement is what, if we actually try to see, we can actually see in terms of this touch counter. So we have this particular parameters which we can actually check out if we really want to play with this. So this LRU link list, it is actually going to be having how much of space allocated for this hot, that is 50% maintained by this. Hot criteria, touch count going to be 2. It can stay in the particular buffer cache, that is going to be 0. Cool count is 1. That means it's actually going to be the decrement value after the buffer is going to be marked as hot. It'll be cool to 1. Aging touch times, that is going to be 3-second timeout. And should we freeze the CR copies in the buffer cache also or not? Obviously, we don't need to. So it is going to be false. It is by default, false. So now there is a clause which is going to be, again very popular, called cache clause, and that is normally understood as that it is going to cache the data in the buffer cache permanently. That is actually incorrect. So we understood already what the buffer cache does. Basically, the buffer is accessed from the disk, and it is actually going to be maintained basically in terms of your particular hot end, and then the counter is actually going to be incremented. Now, when we have the buffer available in the cache clause, or with the table with having the cache clause, the buffer directly goes actually into the hot end. So basically, with the cache clause, the buffer directly goes into the hot end, and again, from the previous discussion, we know it is going to be cooled down, which means buffer, even though it is marked as hot, it cannot remain as hot. So this particular buffer is not cached permanently into the system. It is still replaceable, and it is still susceptible to the eviction. Now, in terms of 12.1 onwards, because of the large objects actually possible, Oracle also have a kind of a separate mechanism for finding out the replacement for the entire object by sort of something called the temperatures, which basically means that, yeah, we can have the present slides. I'll be sending it definitely. So we are going to be having this particular temperature now. So now there is a separate section in the buffer cache, which means that one chunk is maintained for touch count, and the second chunk is maintained for temperature. So again, they basically maintain a value which is actually going to be maintained in a view. So that temperature is actually going to be checked for the objects which you do not really want to maintain by the touch counter. Again, this is done basically for environments where the table size is very, very large. So it is going to be in data warehouse environments. It is available for parallel query, in memory, and rack. So this is how it is actually going to be. So we can have one big buffer cache, and we can decide how much out of it is going to be there for this BTC or big table cache. So we say 3 GB, and the rest of that is actually going to be in terms of the touch count based mechanism. So we can see the temperatures in these views. We can actually see the information of the objects in this. But for this to be working, we need to have the parallelism policy as adaptive or auto, and we cannot have it actually till more than 90% of the buffer cache. Now, the lookup is basically done by this in a very simplified way. Oracle basically finds out the plan. They find out the segment, data block address, look for the buckets, look for the cache buffer chain to actually find out the information. If the buffer is found, it is returned as a logical eye. If the buffer is not found, then they release the CBC latch. They basically read the buffer from the physical IO and put that buffer in the buffer cache using the LRU chain latch, and then give it back to the user. Now, in terms of the tuning part for the buffer cache, there is not much actually required. All what we need to have is that we need to have the buffers to be available in the buffer cache as and when possible in terms of the logical IO. But still, we possibly may have this thing that we can have these kind of problems possible in the buffer cache. For example, we have free buffer weight. Now, the free buffer weight basically means that we are trying to load the data from the disk to the buffer cache, but we don't have the free buffers available in the system. Now, we mentioned that there is a LRU linked list. So the server process which you are using is going to read this particular linked list up to a certain threshold maintained by, again, an internal parameter. And if it can't find the number of free buffers available which you need for your query, it actually gives up. And once it gives up, it basically is going to start waiting in the free buffer wait. And that means that the server process, for example, requires 10 buffers, 10 blocks to be loaded into the memory. It can't find 10 free buffers in the memory. So it gives up, starts waiting on this free buffer wait. And because it starts waiting on the free buffer wait, now the system, the Oracle database, has to immediately make the space available for the free buffers. So DB writer is now going to start writing in the panic mode, which means it does not now wait for the checkpoint to occur. It will start writing immediately. Now, obviously, if this wait event is occurring, that means could be possible we might actually have smaller buffer cache. We might actually have slow writing of the data into the disk. We might not actually have enough number of DB writers to do this particular thing, which means we might want to check it out at different places. Usually, this should not come now, obviously, because we have automation in place, and the storage is maintained in terms of ASM and so. But still, if this is occurring, that means we are possibly having something actually happening for us in terms of either on the storage or on the DB writer numbers. The next one is going to be read waits. Again, not now, but this is still something which makes many DBAs, lose their sleep if they do find out the sequential read, scatter read, and parallel read. Now, these reads, they are actually reported in terms of the AWR, but they are basically the disk read times actually. That means they are basically the disk reads that we are actually having, and these disk reads are basically the one which are actually going to be used by the system in order to actually get the data for us, which means that if we are having this sequential read shown or scatter read shown, for example, it's not really a problem. And the reason for that actually is that uh, obviously in a system we are going to do the reads and we're going to read the buffers nonetheless. So it is not really going to be a problem per se, because it's actually a user IO, and obviously we do not want the users to not do the IO. We actually want them to do the IO. So if this event or these events are occurring, it's not really a problem actually, because they are basically a part of the user IO. But if these events are occurring for a very long duration of wait, more than 15 milliseconds, then it actually can be something which can be a matter of concern. But again, only if it is going to be a continuous behavior. Obviously, it could be possible we might want to read a lot of data. We might actually have slow disks or slow storage actually doing this for us. That is why, if you notice, we are not really actually having this thing mentioned in the terms of other parts, but we are saying that we are going to be having this entire thing available to us in terms of having more capacity or more of these stripes done to the disk, so that we don't have the contention. But they are usually not going to be something which should be considered as a problem if the timing is going to be 10 or under 10 to 15 and it is remaining in that. Latch contentions are going to be there. Now, obviously, we have the data blocks and we have the index blocks contention possible. And mostly, if there is a latch contention coming, it means there is an excessive time spent actually, to search your buffers. As I mentioned before, that the LRU chain latch and the CBC latch, they both represent different contentions. CBC latch contention means that you're trying to read the same buffer by multiple server processes. And if you're going to be having LRU chain latch, it means we're not having free buffers. Now, if it is going to be a cache buffer chain latch contention for data block, maybe someone is trying to do the read access or the read of the same table again and again for multiple server processes, or maybe doing it in terms of a loop kind of thing. That means that it is not really going to be something that we can control by ourselves. Probably we need to go for the application tuning. And if it is going to be an index contention, it again could be meaning that a lot of thing is actually going to be there, which possibly can be changed by creating a different type of index, like maybe a reverse key. If it is going to be buffer busy wait, I'm running out of time, I think. So buffer busy wait is basically going to be more of a cumulative wait. And buffer busy wait actually can occur due to different types of the buffers. Whenever the buffer busy wait actually comes, you do need to check it out that what kind of buffer is in the wait. There are different classes of the buffer. So if you go to $bh or $bh, there is a class column. So if you actually check it out, there is a class 8, class 9, class 10, and many more. There are about 14, if I remember correctly, 14 or 19 something. So you actually need to check it out what kind of buffer it is being waited for, and then based upon that, decide your action. Right, so I'm trying to show it over here. Right now, hit ratio is kind of a dead horse and not really required now, but still hit ratio can be one of the factors to look into if it is consistently being low. If it is not actually, then you should not really pay attention to it. Usually it is going to be maintained in terms of the system for the buffer cache, standard buffer cache, optimally, but the goal is to have in high 90s. So it should be in high 90s, but even if it is not, it's really not actually going to be such a big thing. So the main tuning goals is that you should have it properly sized. AMM should be taking care of it. You should have data accessed by more of logical IOs, less of physical IOs. Obviously, logical IOs are going to be bad itself because they put more contention on the latches. You should not have any weights on the system. And obviously, if you're going to be able to bypass the buffer cache, if you can do the direct path read, which is what Exadata Smart Scan or other such things are actually able to do, that is going to be better. So this is, most of the stuff is now automatically done. We have the DB cache advisor to talk about the size in case required. So 10% to 200% of the buffer cache, the size actually can be recommended, or we can use AMM or ASMM. ASMM is 10G or before. AMM is actually much better. As I mentioned, that if you can bypass the buffer cache, for example, using a direct path IO thing, it's actually going to be better. So that concludes the session. I think barely on time. How much time we left for the question answer? I think 5 minutes. Or are we done with the time? Okay, let me quickly check. We have a table with 3 lobs. Vendor has recommended to recreate the table with the multiple block size 2K, 4K and use the default 8K. This is based upon lob length. Lob will be storage out of row. Will this benefit or harm in long term? Kind of a, it should be okay. It should not really be a problem. It's too less actually to be mentioned. Like in terms of performance, I don't think that it's really possible to be told that having this default K and the multiple block size 2 KB and 4 KB, there will be any performance impact actually, because the caches for the 2 KB and 4 KB mir are going to be separate. So it should not be a problem as far as it looks like. Okay, so we have Wasim. Yes, Wasim. Sure, no problem. I have too many row lock contentions on select for update. Select for update is actually going to be locking your table. So if you're doing it, unless you're not really requiring to do a where current off in your code, you possibly shouldn't actually be doing this select for update, Wasim. It is actually going to be an additional lock that you are implementing, unless you don't need it. Like only reason I normally see it is in terms of where current off, but if you're not doing it, there won't be any other reason to use it. So maybe you want to check it out why you're doing it. No problem. Okay. Yes, Roman, please. I don't see the question. Okay. Buffer busy wait. Okay, so buffer busy wait, got a question. Could you explain more on a buffer busy wait? Well, the thing is, see, very quickly, if I have time. So take it like this, that I have a segment, and this segment has a header block. Now, everyone, let's suppose this is one session, this is second session, and they are looking for the block to be available to do their insert. Now, because they're looking for the free block, and we are taking example of free list, they're looking for the free block. They need to access this free list. To do this access, the first point of entry is going to be the header block. So the process 1 enters into the header block, process 2 enters into the header block. Now, if the header block has two, let's suppose, transaction slots, and both are occupied, now if the third one comes, it cannot actually do the work in this same particular header block. So now this third process is going to log the buffer busy wait. Now this buffer busy wait is happening for which particular type of the block? It is happening for the segment header. Similarly, there could be a wait for data block header. There could be a wait for data block itself. There could be a block wait for the ASM type 1, ASM type 2, and so forth. So what I meant actually, that buffer busy wait is a cumulative wait. It will show you the file number, it will show you the block number, and an ID, which is going to be a 3-digit number. And from there, you need to figure it out that what kind of is the reason that you are having the wait. Based upon that, you need to decide your course of action. So it is basically a block wait, but for which kind of wait, which kind of block it is happening, that you need to actually figure it out. Does that answer your question, Basim? Okay, any more questions? I think, okay. Yes, please. Who raised the hand? Yeah, Basim, go on, please. Okay, Sharik, sure, no problem, no problem. Yeah, I just explained buffer busy wait already. I think it should be clear. Great, thanks. I think we are most likely out of time. Everyone, in case you want to follow me and want to have more discussions, I'm on Twitter. Do follow me there. I think that's much better place to actually have a communication or a discussion. How much time we have left? Okay, we got some more questions coming up. May I know if the recording will be shared? I think it should be. I'm not the best person to answer this. I think it will be dependent on the organizers. So will it be shared? The recording will be shared with the
Yes,
participants?
yes,
Okay,
we will share it on YouTube channel coming
right,
days.
right. How much time we have left? I think we are almost done.
Yes, I think yes. If you have a question, we don't have any question, right?
Yes, I don't have any question in my open list, I think. Okay, Wasim, yes. We have about 2 minutes, I think, left.
Yeah, in 2 minutes we'll close. Yep.
All right, just a quick reminder, everyone. Let me clear this out so that for people actually can see. So I'm on this handle. In case you have any question which I could not answer or if you could not ask, do come back on Twitter. I think that's going to be the best place to have the communication, and not many other people are there too. So I think possibly that's going to be the best place for the questions. Okay, let's see. We have in general all memory management with Oracle, all memory managed by Oracle with its latest version. Do we still need to worry about memory management? Well, yes, it is something that we can't ignore. The effort is not much now. We don't really need to micromanage it, Sunil. We don't need to micromanage it, but we still need to manage it. I mean, you can't say that just because I'm using AMM, I will never have any memory issues or memory errors. But it is better than micromanaging each parameter one by one.
Aman, I think the last question. Sanyal said the question.
Yeah, I just answered. So I think we are out of time now.
Yes.
Okay. Well,
Thank you, Aman, for
thank
interesting,
you, thank you,
accurate
thank you so much for
presentations.
having me. Thank you so
We
much.
are
Thank you so very
we are
much.
very
Thanks to everyone who
grateful.
joined in.
Yeah, we are looking forward to your new presentations for future events.
Thank you so very much. Thank you so very much.